All right, moving on to between sample variability and within sample variability. Within sample variability is the variability of each sample. So that's the variability that occurs between each of these. Between is the variability among the sample means. So if you calculated each of these means, add these together and divide by the amount of numbers that are there. This would be 5, this would be 8, and this would be 11. The between sample variability is the variability between the means. What evidence will suggest that samples come from populations with different means? If the between sample variability is large relative to the within sample variability, we have evidence to suggest that the samples come from populations with different means. So this is a good indicator that they're going to be from different means, but like we've done in the past, we're still going to want to do our hypothesis testing. So just looking at the between sample, comparing it to the within sample variability is going to indicate, but you still want to do the hypothesis test, which we're going to start with on the next page. Here are the 6 steps for computing the F-test statistic by hand. Step 1 is compute the sample mean of the combined data set by adding up all the observations and dividing by the number of observation. Call this X bar. So let's do that right now. So add up all these values and then divide by the number of values. So we have 4 plus 5. And then divide by 15. There's 15 numbers. So X bar is 8. Step 2, find the sample mean for each sample. Let X bar sub 1 represent the sample mean of sample 1. X bar sub 2 for sample 2 mean, and so on. I have typed the list into list 1, 2, and 3 for the corresponding samples. Now if you recall from number 1 on our calculator sheet, the 1-var stats will give you the mean, the standard deviation, your sample size, etc. on that page. So X bar is 5. And then step 3 also wants you to find the sample variance for each sample. Remember, the sample variance is your sample standard deviation, 1, in this case, squared. 1 squared is 1. Then you can do it again for your second list. So L2. 8 is our mean. Again, our sample standard deviation is 1. When you square that, you get 1. And then the third list, mean is 11. Sample standard, or the variance, we're going to square 1.2247. And it is 1.5. Step 4, compute the sum of squares due to treatment, SST, and the sum of squares due to error, SSE. So here you can see SSE is the top portion of this fraction. So what you're going to do is plug in your values. So what's the sample size of your first sample? There are 5 numbers minus 1. And then what's S sub 1 squared? 1. And then you do the same thing for the second sample. Again, there are 5 numbers, and the variance is 1. Again, 5 numbers minus 1, and the variance is 1.5. When you put that on your calculator, you should get 14. So then we need to do SST. And now that's going to be the portion on the numerator for that one. So again, the value or the number of values in your first sample is 5. Your x bar sub 1 is 5 minus your x bar 8. And then repeat that again for your next 2 samples. So 8 minus 8 squared plus 5 times 11 minus 8 squared. When you put this on your calculator, you should get 90. This k just means to your last sample size. So this is just a generic formula. So we could have substitute 3 in for your k, and that's how you would have got these last numbers to match up. Step 5, divide each sum of squares by its corresponding degrees of freedom, k minus 1 and n minus k respectively, to get MSTE and MSE. So MSE, so first, actually let's do MST first. MST is SST, so you're 90, divided by k minus 1. So k is the number of samples. So 3 minus 1. So it's 90 divided by 2, which is 45. Then MSE is your SSE divided by n minus k. So 14 divided by n is the actual total number of samples taken. So 15 minus your k again was the number of samples, 3. So that's 14 divided by 12, which is 1.1667. Step 5 is to compute the F statistic. That is the mean square due to treatment divided by the mean square of error. So MST divided by MSE. So it's 45 divided by 1.1667, which is 38.57 is your F statistic. So this next table, it sums up what we just did. If you added these degrees of freedom, so k minus 1 plus your n minus k, your k's cancel, right, because they're opposite. You're left with negative 1 plus n, and that can be rearranged as n minus 1. So that's how we get to that total. If the p-value is less than the level of significance alpha, reject the null hypothesis. What calculator command can we use? That would be number 22. All right, we're still working with the same example. The question now asks, do the data suggest that there is a difference in the mean shear bond strength among the 4 treatment groups at the alpha equaling 0.05 level of significance? So here we're going to do our hypothesis testing. There are 5 steps. Remember, the first step is to state the null and the alternative. The null is that each mean is equal. So you could actually write that out in a sentence, or you could write it out like this. And the alternative is that at least one population mean is different than the others. Step 2 is your alpha. Step 3 is to find your test statistic and your p-value. So number 22, type the data into list 1 and list 2. You can see here the data is in list 1, 2, 3, and 4. We already checked the requirements, so it's done. Now we can go to part C here, go to Stats, Tests, ANOVA, and then enter all the lists it is in, separating them by a comma, and then after the last one, end the parenthesis and hit enter. Here our F test statistic is 7.55. And our p-value was 0.0023. Right underneath. Step 4 is compare your p to your alpha. It is less than that, so we reject the null. And then step 5 is to state the conclusion. So we can say there is sufficient evidence at the alpha equaling 0.05 level of significance to indicate that at least one population mean shear bond strength is different from the others. So if you were a dentist, this might be helpful. Okay, so we know that these are not all equal. We know which one's different. However, we don't know which one. So whenever performing analysis of variance, it is a good idea to present visual evidence that supports the conclusions of the test. Side-by-side box plots are a great way to help visually reinforce the results of the ANOVA procedure. When we reject the null hypothesis of equal population means, as in the last example, we know that at least one population mean differs from the others. However, we do not know which means differ. Side-by-side box plots can give us some idea, but we can more formally answer this question using Tukey's test, which will be discussed in the next section. However, this is not covered in this course, and this is actually the end of this course. So if you do want to know more about that, you could always reach out to me or do some research on your own. If you have any questions, please email me or post to the discussion.